Okay, guys, I want to go over just a little bit of the energy that has calculus in it, and then potential energy curves, because that's also something that we didn't cover. We'll see this mostly on multiple choice questions, but there's an interesting relationship between the force and the potential energy that I want you to be familiar with. So, in general, we know that the work is going to be the integral of the force with respect to the change in the position. So this is the work done by a variable force. If you look on the notes, we have this problem where they're telling us that we have a force that is 3x squared newtons in the I hat direction and 4 newtons in the j hat direction. This I and j is x and y. So in general, if we're talking about what our directions are, our x-axis, if we talk about it as being a unit vector, it gets an I. Our y direction, if we talk about it being a unit direct vector, it gets a j. The hat on it just tells you that it's a vector, and those are 1 unit long. I'm going to bring this a little bit closer. I get a limited number of videos on this, so that was worse. There we go. All right, so we have a function that is going from 2 meters to 3 meters in the x direction, and a function that's going from 3 meters to 0 meters in the y direction. And they're asking us how much work is done on the particle as it moves like this. You'll never see one like this. They'll always keep it to 1 dimension, but this was from the textbook. So we're going to have individual integrals for the force in the x direction with respect to the change in x, and the force in the y direction with respect to y. And so for our x direction, this is going to go from 2 to 3. So I'm going to make it go from 2 to 3. So we have a definite integral. And then I should have written this one a little bit lower, so I had a little bit more space on that. And this one is going to go from 3 to 0. I'm going to plug in what they tell us the function is. So this is our f of x ends up being 3x squared. We don't need to include the I hat in there. Dx, and from 3 to 0 is going to be 4 dy. So we can leave that out if you want to, or leave it inside the integral. It doesn't matter. So if we do the integral of this, it's going to be x cubed from 2 to 3 and fy from 3 to 0. And you can see on your paper, they're telling us what our values would be. And when I add the two of them together, I'm going to end up getting 7 joules. So this would be 27 minus 8. And this would be 12 minus 0. and this is going to give me 7 joules. It's good to keep in mind that this is a dot product, and to remember that for power and work, this is a multiplication of 2 vectors that results in a scalar. So whatever answers we get, we can just add them together. The positive result tells us that we are getting energy transferred to the particle by the force, and the kinetic energy increases because the kinetic energy is equal to 1/2 mv squared. So it also must increase. If it would have been negative, then we would have had a loss of energy. All right, so we can also think about power as the rate of change of work. This is also going to be a scalar, and it is going to be equal to the dot product of the force and the velocity. It's rare that you're going to see a power problem. Almost exclusively, it would be just one multiple choice or no multiple choices. And it'd be even more rare for you to see one where you'd actually have to do calculus. But I want you to be familiar with what that looks like. And we can see here that we have this FV cosine of phi. Again, when we have a cosine, they're telling us that we're combining parallel components. We see the dot in the middle that tells us it's the dot product. So this is going to be vector multiplication that results in a scalar. And those are the only 2 dot products you guys have, but there's more in magnetism if you go on to study that. I just want to see how power shows up on here. If it is, yeah, they have power on your equation sheet written as the dot product of the force and the velocity, and then also as the derivative of energy with respect to time. And again, energy and work can be interchangeable. All right, so we know that this work is going to be this integral from one to the other of fx dx. This is going to give us an area. I want to connect this to change in potential energy, which they often do, and then show you some potential energy curves, which once you know how to read them, the problems are really easy. But if you've never seen one before, it doesn't make a lot of sense. So if we have work that is parallel, we can change the energy. So I know that if I apply a force in this direction up, that I'm going to do positive work. How do I know that it's positive work? Because I increased the energy, and also my force and my displacement are in the same direction. Gravity, on the other hand, as I'm displacing it up, would be doing negative work because that force and the displacement are in opposite directions because gravity is always down. So I'm going to raise it at a constant speed. So that's going to tell me that I have F net equals 0. So how much I push up is exactly how much goes down. And I know that my work applied is going to be equal to my change in potential energy, which we write as delta U little g. And we're going to keep big G for when we're talking about things that are on asteroids or on planets where we're really changing what our gravitational field is while we go. So if we have it moving at a constant speed, the work done by gravity is going to be negative our mgh. And so the work done by gravity is opposing the increase in potential energy. So we're going to say that the work done by gravity is negative delta U. If I look at it another way, what happens if I let go of the ball? It's going to go back down to the ground. As it falls, gravity is now in the same direction as what my displacement would be. So it would be doing positive work as it went down. So the field that it's in this case a gravitational field, is always trying to reduce the potential energy. So now that I know what this is, and I know that the work done by the field is going to be the negative change in potential energy, we get this relationship that our change in potential energy is going to be equal to the negative of this integral. And you really want to think about what is the relationship between the signs of the potential energy and what the work is. So if the potential energy is our antiderivative, just another name for integral, I can go in the opposite way and I can say that the derivative of u with respect to x is going to be equal to negative fx, or fx is going to be equal to negative du dx. And I know when I'm talking about derivatives that I am talking about slopes, because they're going to ask us places where we have equilibrium, and equilibrium is going to be a slope of 0. So slopes of 0 should be easy for us to pick out when we have these potential energy curves. And the first ones they show you make sense. This is not on the equation sheet, so you're just going to have to know that you have this negative relationship. So the area of this is going to get us the work done by that force. If I take the negative of the area, it's going to give me the change in potential energy. All right, so there are 3 that you could have in potential energy curves. I'm going to have you guys watch a short video, and way shorter than my videos are always. I think it's like 7 or 8 minutes, where they're going to go over potential energy curves. The weird thing to me is in a potential energy curve, they'll have all sorts of values on the curve that whatever energy you have never reaches. So you can only worry about where you can actually exist on the curve. You can have one that is stable. You can have one that is unstable. You can have one that is neutral. Equilibrium is going to happen when we have F net equals 0. So if I want to find where this point of equilibrium is, I'm looking for places where there is a slope of 0. So here is a stable equilibrium. I can see that I have a slope of 0 right there. And then if I have this amount of total energy and I were to release whatever this is, it would be able to stay in this without falling out of the system. That's what makes it stable. At any given point, if I want to get what the force is, I would take the slope and then I would take the negative of that value. Unstable would be one that looks like this. So here's our skater again. At any given side of this, it would go down and be off of our curve. We would have potential energy decreasing from any point off of the unstable one. For the stable one, any point that we would go off of our equilibrium point actually increases the potential energy. And then here they have an example of a neutral equilibrium. So we have a slope of 0 for this stretch through here. And if I were to push it a little bit this way or push it a little bit that way, nothing would happen until I went past this neutral place. So again, they have a picture here of what's going on. All right, so this is what the potential energy curve is typically going to look like to you. Very often they'll have a grid to make it more like a graph. So if I have a system and I could say that this system has a total energy, let's pick something, of 3.5 joules. So that is going to be my total mechanical energy. They might ask you at different places, what is your potential energy of position and what is your kinetic energy? These two added together are always going to have to be 3.5 joules. So at x1, I would say my potential energy is 3.5 joules, which would make my kinetic 0. At x2, I'm down here. At this point, I have no potential energy. It's 0 joules. And now my kinetic is all of these. x3, I have both. So at x3, I have a potential energy that lines up with the 3 joules, and my kinetic is 0.5 joules. So they could ask you, like, what is the speed at x3 if the mass is 1 kilogram? And you would have to take this 0.5 joules, and you can set it equal to 1/2 mv squared. And then if we look at x4, I'm at 1 joule for potential. And so kinetic would have to be 2.5 joules. So even though this goes up to 6 over here and up to 4 over there, the amount of energy that I actually put in the system is actually just going to go from here to there and then back. So even though you have values that are outside of it, you can never reach them, which is weird. I don't understand why they don't just have the actual graph be whatever it is, but that is not the case. If they ask us what the force is, then we have to look at our slopes. So if I have a positive slope here, that's going to tell me how it's changing. I'm going to know that I have I see what's going on. They're going from, they're taking the slopes here and they're plotting it over here to make sure, to show you what it looks like. So if we look at x1, remember that negative du dx is going to be equal to my f. If I look at where I am at x1, this is a negative slope. And if I take the negative of that, I'm going to get a positive. And so they plot this as a large force in the x direction. So I have to recognize that a steep negative slope means a large positive slope, positive force. And some place where I have a positive slope would be the opposite. So I have a positive slope here, this is going to be a negative force. And if I go over to where it is after x2 before x3, that tells us that we have a negative force. So a positive slope gives us a negative force. If I look at where my slope is 0, that's going to represent a force that is 0. So I have a force of 0 there, and I have a force of 0 there. So those were plotted, and then you just have to take the opposite of the slope. So they're saying that if they had a flat line, it's going to give us a total mechanical energy that's equal to this 5 joules. And then just like I did at all the different positions, if I take what this is minus where you are, the kinetic energy has to make up the difference. So they're saying that this is our 5 joules of mechanical energy, and they're saying at this point here, that's at 4 joules of potential, then I must have 1 joule of kinetic. And they have moving graphics in the video that'll hopefully make a lot more sense. And then whether it's trapped or not is if it has enough energy to get out. So this particle here only has 5 joules. It can never get out that way, but it would be able to get out on this way here. In this one, they had 4. The example I gave you had 3.5, which would just have you trapped in there. So this 4 would get us just in that. All right, so hopefully that made some sense, that we're starting off just with our work as being the integral of the force with respect to position, which is going to tell us that the change in potential energy is going to be the negative of this. So the negative derivative of this position is going to give us the forces. So if I'm looking at the slopes, a positive slope on my U graph is going to give me a negative force. A slope that's negative on my potential energy graph is going to give me a positive force. A slope of 0 on my potential energy graph is going to give me equilibrium. And then the mechanical energy is constant. And so at all times, these two have to add up to whatever they tell you it is. And then, like I said, the only other thing they might ask you is how fast it's moving when it gets at a certain point. You would have to just set whatever energy is left for being kinetic energy into 1/2 mv squared. Like I said, there'll be a second video that goes along with this that's an Ed puzzle that asks some questions on the topic.